Hello students, in this video we'll find the Schwarz-Christoffel transformation for a degenerate polygon which corresponds to puncturing the plane by half of a strip. So let's consider the region R described geometrically. In the following way. So what are we going to do? We're going to take a point over here. This point's going to be I times tau. We're going to look at the negative of that, the complex conjugate of that, negative I tau, where tau is a real number. So let tau be a positive real number, okay? And then we're going to connect those 2 points over there. And we're going to let that go to all the way to infinity, right, along that line, right? So this point would be like negative tau, I tau, plus infinity, right? Plus infinity. Over here as well. And our region is going to be the complement of this region. So I punched out this region from the complex plane, and our region R is now going to be everything outside this region. So there's a fluid, and we imagine there being a fluid because we can think of this in terms of the streamlines of something that's on the complement of a box like this, okay? So that's our region over here. I want to investigate the streamlines, right? How do the streamlines move of an incompressible, envisaged sourceless, irrotational fluid that basically tries to move around this like box, this barrier over here, okay? Good. All right, so now, of course, this is a degenerate polygon. So note, this is, of course, in our scheme, note, this is a degenerate polygon. Okay. And it's not convex. And moreover, convex. Okay. All right, because of course if I draw a line from this bottom to the top, I get outside the region, right? Excellent. So there's two exterior angles in this region, right? There's this exterior angle over here. That's my alpha. That's my beta. They look like they're the same, right? And what's the key feature? The key feature is that I know that alpha plus the interior angle, and the interior angle in this case is 3 pi over 2. 3 pi over 2 has to equal pi, which forces alpha to be negative pi over 2. So it's a negative exterior angle. And similarly, beta plus 3 pi over 2 equals pi forces beta to be the same thing. Beta is going to be negative pi over 2. Now, negative exponents correspond to positive parameters in the Schwarz-Christoffel, right? These will be positive exponents in Schwarz-Christoffel. Okay, excellent. Now, I'm going to choose things in such a way that I'm going to take z equals negative 1 is going to be mapped to I tau. And then z equals positive 1 is going to be mapped to I tau. Okay, so I'm going to map negative 1 to negative I tau and positive 1 to positive I tau. What will the Schwarz-Christoffel mapping be? F prime of z will be a constant, a parameter a, right? And then it's going to be z plus 1 to what power? Now the power is positive a half, and then z minus 1 to the power positive a half, right? So I get an a, then a z squared minus 1 to the 1/2 power. That's the derivative. And remember from previous videos that if I can integrate this, I can find the function, the complex potential. The imaginary part of the complex potential being constant corresponds to the streamlines. So for a function like this, I can use Calc 2 techniques to integrate, right? Because I know by analytic continuation that any formula I get for the antiderivative, if I did this over the real line, would have to be the same exact formula in the complex plane, which is beautiful, right? So I'm going to leverage that more theoretical device to do this cool application, right? So let's find f, right? What's f of z? Now we got to use our Calc 2 techniques. It's going to be a, the integral, square root z squared minus 1 dz, okay? This is sort of classic hyperbolic substitution. You can do secant, but you're going to get the same thing, right? So this is going to be equal to a, the integral, square root, z is going to be cosh. So cosh squared zeta minus 1. Derivative of cos is sinh, right? d zeta. Good. Now cosh squared minus 1, I know that cosh squared minus sinh squared is equal to what? Cosh squared minus sinh squared is equal to zeta. So cosh squared minus 1 is equal to sinh squared, right? So that's sinh. So this is going to be a, the integral of sinh squared of zeta d zeta. Okay? Good. Now to use the double angle, I have to do power reduction for sinh. Power reduction for sinh is going to be cosh of 2 zeta minus 1 over 2, right? That's sort of easy to, that's easy to prove, right? That's an easy formula to prove. You just multiply by 2 and then square everything out, right? Excellent. Okay, so that's the double angle formula, or the power reduction formula, right? It's only slight variations from trig, and trig would be the opposite sign, right? And this one stays this way. So it's going to be A, and then we're going to have what? We're going to have a sinh of 2 zeta over 4 minus zeta over 2 plus a constant b. Okay, good. Now, let me incorporate that 2 into the a, right? So it's going to be a over 2. And then sinh of 2 zeta is going to be 2 sinh zeta cosh zeta. So the 2's are going to cancel out over there. You're going to have sinh zeta cosh zeta. And then you're going to have a minus zeta plus b. Okay, now figure out what these things are going to give us. So plugging back in, this is going to give me what? This is going to be a over 2. And then the sinh is cosh is just going to be z, right? And we saw that before. That's just z, square root of z squared minus 1. And then minus zeta, which is the what? So the cosh of zeta is equal to z, so this is going to be minus the inverse cosh. The inverse cosh is the log of the z, that's just regular complex branch of a log, plus square root of z squared minus 1 plus b. Now I got to find those parameters over there, right? So now I know that f of negative 1 is going to go to I tau. So f of negative 1 is going to be negative I tau, negative I tau. So what happens when I plug in negative 1? This term's going to vanish. When I plug in negative 1 over here, I get the log of negative 1, which is I pi. So it's going to be an I pi. This is equal to a over 2. And then I'm going to have the log, I'm going to have minus log of negative 1. The log of negative 1 corresponds to I pi, right? So that's going to be a negative I pi, like that. Good. And then plus b, like so. F of 1 is equal to I tau. And so what's that going to give me? That's going to give me an a over 2. When I plug in 1 over here, I get 0. When I plug in 1 over here, I get 0, right? So there's nothing over there. So it's a over 2 times 0. And then plus b, right? Plus b. Good. So of course that says that b is equal to I tau. Okay. And then of course what we have over there is that the first equation tells us what? It tells us that negative I tau is equal to a over 2, negative a over 2 I pi, right? And I can put that negative 2 over there because I know what b is, right? So the negatives are going to cancel out, the i's are going to cancel out. So I'm going to have 2 tau is equal to what? 2 tau is equal to, the i's and the negative cancel out, a over 2 times pi. So a is going to be what? A is going to be, let's see, so a is going to be 4 tau over pi. 4 tau over pi. Okay, great. And therefore we have our solution, right? So if a is 4 tau over pi, this is going to become what? So a is 4 tau over pi, kill 1 pi is going to get 2 tau over pi, so 2 tau over pi, and then z square root z squared minus 1 minus the log of z plus the square root of z squared minus 1, then plus b, which is I tau. Beautiful. There we have our formula, right? So this is the conformal map, which takes the upper half space, onto the component of this region, right? Beautiful. Moreover, what do I know? Moreover, I know that if we do the standard thing, right? If I replace z, so if I replace z with t plus ic for t and r, those give me the streamline. So if I take z and replace it with t plus ic, I'll be able to simulate what the streamlines look like. I encourage you all to do that, right? I don't have a computer here, otherwise I would just type it in, right? But if you have a computer, well, if you have some like Desmos or whatever, plug those curves into this function, see what you get. You're going to get these beautiful curves that move around this bend in a very particular way, and those have to be the streamlines for an incompressible irrotational flow in the plane. Beautiful. Thank you very much.